Hello students, today we will revise the unit number 1, that is per gear. First we see the terminology of spur gear. If we consider the two teeth from the total spur gear, for understanding purpose we draw the maximum size for this teeth, and now we discuss the terms one by one. If we draw the circle, imaginary circle between the teeth, then this circle is called as pitch circle. If we draw the circle from the top portion, that is called as addendum circle, and the circle which is drawn from the bottom portion, that is called as dedendum circle. The distance of tooth which is parallel to the axis is called as face width. This is from here to here. This is indicated with a letter B. Then top portion of the tooth is called as top land, and the bottom portion of the tooth or bottom portion of the gear is called as bottom land. Now we see addendum and dedendum. If we consider the radial distance from the pitch circle up to the addendum circle, this is called as addendum, and the distance between the pitch circle and dedendum circle, this radial distance is called as dedendum. Then if we consider the pitch circle, along the pitch circle if we measure the distance of tooth, then that distance is called as tooth thickness, and the distance between two teeth is called as space width. This distance is also measured along the pitch circle diameter. If we add tooth thickness and space width, then this total addition is called as circular pitch, and this circular pitch is also measured along the pitch circle diameter. If we consider the pitch circle diameter, and if we consider the surface along that pitch circle diameter, then surface above that, if we consider this is the boundary for that surface, then above this line or above this surface is called as face, and below this surface is called as flank. Now if we consider the important points in this terminology, then pitch point, it is the common point of contact between two pitch circles. Meaning is that if we consider the two circles which is in meeting, then always we consider the pitch circle diameter is important, and these two pitch circle diameters are meeting with each other at the one point, and that point is called as pitch point, and through this pitch point all load is transmitted from first gear to the another gear. Third is pressure angle or angle of obliquity. It is represented with symbol phi. It is the angle between the common normal to two meshing teeth at the point of contact and common tangent to pitch circle at the pitch point. Standard pressure angles, that is 14.5 degree, 20 degree, 22.5 degree, 25 degree. These are the standard pressure angles. The most widely used pressure angle is 20 degree. Circular pitch, we already discussed about this. Circular pitch is the addition of tooth thickness and space width, and this distance is measured along the pitch circle diameter. This is called as circular pitch, and it is indicated with letter PC. If we see the formula for circular pitch, then circular pitch is equal to pi into d upon z, where this PC is circular pitch, d is pitch circle diameter, and z is the number of teeth. Next important term is module, which is indicated with letter M. It is the ratio of pitch circle diameter in millimeter to the number of teeth. Mathematically, M is equal to d upon z. But we know that circular pitch PC is equal to pi d upon z, and by using this relation d is equal to m into z, so in place of this d we substitute m into z, so PC is equal to pi into mz upon z. This z gets cancelled, therefore PC is equal to pi into m. Now if we calculate the module value, and if that value comes in point, then we take next standard value from this table, and two different choices are there, that is first choice and second choice. If we see the first choice values for module, this is recommended by ISO, and these values are in mm. First choice becomes for m is equal to 1, 1.25, 1.52, 2.53, 4, 5, 6, 8, 10, 12, 16, 20, 25, 32, 40 and 50, like that. Second choice is 1.125, 1.375, 1.75 up to 45. The first choice models are preferred mostly. Next is diametral pitch, that is PD. It is the ratio of the number of teeth to the pitch circle diameter, that is PD is equal to Z upon D. PD is equal to 1 upon module, because module is equal to D upon Z. So substituting in place of D upon Z M, so PD is equal to, that is diametral pitch is equal to 1 upon module. We already see addendum and dedendum, that is represented with HA and HF symbols respectively. Total depth is the radial distance between the addendum circle and dedendum circle, means total depth is equal to addendum distance plus dedendum distance, that is HA plus HF. This is called as total depth. Next is flank of the tooth. It is the surface of the tooth below the piece surface, and face of the tooth, it is the surface of the tooth above the piece surface. We already see this in diagram. This portion is called as face and this portion is called as flank. Face width B, it is the length of the gear tooth measured along a line parallel to the gear axis. This distance is called as face width B. Speed ratio or gear ratio, which is indicated with symbol capital G. G is equal to number of teeth on gear divided by number of teeth on pinion, that is ZG upon ZP. We want to convert this into diameter format, so which is equal to, we multiplied and divide by m, so m into ZG upon m into ZP. But we know that diameter is equal to module into number of teeth, so m into ZG is DG, m into ZP is DP, so G is equal to NP upon NG. If we have the speeds of pinion and gear, then we can easily calculate by using this relation, that is gear ratio is equal to NP upon NG. Next is center distance A. If we consider the two gears, like in this figure, this is first gear and this is second gear. If this is the center and this is the center of second gear, distance between these two centers is indicated with letter A, and this is the center distance. So A is equal to pitch circle diameter for pinion plus pitch circle diameter for gear divided by 2, that is dP plus dG upon 2. But we know that D is equal to m into ZP. So dP is m into ZP and dG is m into ZG divided by 2. Here m is common, so we take m outside the bracket, so in bracket ZP plus ZG divided by 2. If we convert this ZG in terms of ZP, then it is also possible by using this relation, that is G is equal to ZG upon ZP, therefore ZG is equal to G into ZP. In place of ZG we substitute G into ZP, so ZP is again common, so m into ZP into bracket 1 plus G upon 2. So in this way we finish here the terminology. Now we see the force analysis of spur gears. If we consider this becomes the free body diagram. These two gears we consider, and in actually these two gears are in contact with each other, but for showing the forces we separate these gears, and we draw the free body diagram. This is not actual gears, but pitch circle diameter we shown in here. So basically two different types of forces are acting in case of spur gear. One is radial force and second is tangential force. If we see the important force which transmits the rotation or torque is tangential force. So important force in spur gear is tangential force. If we observe the radial force direction, this radial force direction acts towards the center of the respective gear. So if we consider this is the driven gear and this is the driving pinion. So in case of here upward gear, this Fr acts upward direction, means radial force always acts towards the center of the respective gear. So if we consider upper gear, then this Fr acts in upward direction. If we consider Fr for driving pinion, then in this case it acts in lower direction or downward direction. If we see the tangential force, for tangential force, observe which gear is driving gear. In this case, this gear is considered as driving gear. Then observe the direction of rotation. In this case, driving gear having the direction of rotation is clockwise direction. Then mark the tangential force which oppose the direction of rotation of driving gear. So in this case, if direction of rotation is here, so we act Ft on left side, so it easily oppose the direction of rotation. But in case of driven gear, this concept is opposite. In case of driven gear, if the rotation is in anti-clockwise direction, then Ft component supports this direction. So this is the directions to decide for forces. If we see the relations, so for tangential force Ft is equal to power upon pitch line velocity V, which is equal to torque on pinion divided by dp upon 2, which is equal to tg upon dg by 2. So the tangential component of force Ft acting on the driving pinion. So tangential force is equal to torque acting on pinion divided by radius on pinion, which is equal to torque acting on gear divided by radius on gear. And the radial force, that is Fr, is equal to tangential force Ft into tan of phi, where phi is the pressure angle. If we see the resultant force, then F is equal to under root of Ft square plus Fr square. One more relation is equal to Ft upon cos phi. So this is about the forces acting in case of spur gear. If we see the next, that is design procedure of spur gear, the different steps are there. So first we start with beam strength calculation. This is the step number 1. So beam strength calculation, or beam strength, is nothing but maximum tangential force acts on the gear tooth before bending failure. So Fb is equal to sigma b into p into m into y, where sigma is permissible bending stress in Newton per mm square. The sigma b is equal to Ka into Kb into Kc into Kd into Ke into Kg into Se dash, where all this Ka to Kg is the factors which is considered in case of gears. So all this value or all this combined value becomes 0.66. Se dash is nothing but endurance limit, which is equal to 0.5 into ultimate tensile strength, that is SUT. So sigma b is equal to this 0.66 into this 0.5 into this SUT. So if we multiply this, then sigma b is equal to 0.33 into SUT. So we write this 0.33 as 1 upon 3. So sigma b is equal to SUT upon 3, where SUT is ultimate tensile strength. So this is about the sigma b calculation. Then if we see the second term in this beam strength equation is b, and this b is the face width, and face width is this axial direction thickness of the tooth, that is b. The face width of the gear is taken between 9 and 15 times the module, that is in this range. 9 times module is less than or equal to b is less than or equal to 15 times module. If this information is not available, then directly you consider b is equal to 10 times module. Then m is the module, y is called as Lewis form factor. This equation is developed by the scientist named as Lewis, and so it is called as Lewis form factor. This Lewis form factor y depends on three different terms, that is number of teeth, tooth system, point of application of load. The values of Lewis form factor for different tooth systems for the load conditions are given in table number 1. So if we consider this table number 1, the column headings becomes number of teeth, then second heading is 14.5 degree full depth involute, and second heading is, third heading is 20 degree full depth involute. So if we consider number of teeth becomes 10, then for 14.5 degree full depth involute or composite system, we take the value becomes 0.1759. If the 20 degree full depth involute system is there, then we take 0.2011 is the Lewis form factor Y. For number of teeth 12, 14.5 degree full depth involute 0.2105, and for 20 degree full depth involute system Y is equal to 0.2450 up to 300. This table is available in book, so due to space limitation here I written only 3 terms. So for 14.5 degree Y is equal to 0.3833, for 20 degree full depth involute Y is equal to 0.4712. But if this table is not available, then some empirical equations are also available. So for 20 degree full depth involute Y is equal to 0.484 minus 2.87 divided by number of teeth Z. For 20 degree stub involute system, take Y is equal to 0.55 minus 2.64 upon Z. For 14.5 degree full depth involute and composite, Y is equal to 0.39 minus 2.15 upon Z. So here we see all the terms, but two gears are there, so pinion and gear. So which gear which values we substitute here for beam strength calculation, whether we substitute pinion or whether we substitute the gear values. For that purpose we consider the product of sigma b into y for pinion and sigma b into y for gear. If sigma b into y for pinion is less than sigma b into y for gear, then we substitute, or we consider pinion is weaker in bending, so we substitute pinion values in this equation. But if this product for gear is less, sigma b into y for gear is less than sigma b into y for pinion, then we substitute gear values in this equation. So according to this comparison we substitute here. Why we consider sigma b into y only? Because b and module is same in pinion and gears. So sigma b, if the different material is there, then sigma b is different, and y depends on number of teeth, so y is different. Step second. In case of step second, that is wear strength calculation, if we see the definition, the maximum tangential force before the wear failure, that is called as wear strength. So if we consider wear strength, equation it becomes Fw is equal to dp into b into q into k. So always this term becomes dp, that is piece circle diameter for pinion. Whether in case of first that is beam strength calculation, whether pinion is weaker or gear is weaker, that is different, and this equation is different. So always here piece circle diameter we consider, that is dp. So if we consider here this term, b is the face width already discussed, q is new term, that is ratio factor, and k is a load stress factor. If we find out ratio factor, the equation becomes 2 into number of teeth on gear divided by number of teeth on gear plus number of teeth on pinion, that is 2 zg upon zg plus zp. This is for external gear pair. Means if we consider this is one gear and this is another gear, then this connection is externally connected. So for that purpose here we use this equation, that is 2 times zg upon zg plus zp. If gear is internally connected like this, if this is first gear and this is second gear, then in this case here only slight difference is there. In place of plus sign, here we take minus sign. This is the only difference. Here in case of external gear pair this is plus sign, but in case of internal gear pair this sign becomes minus. Then load stress factor K depends on material. So three different cases are maybe there, that is for steel pinion and steel gear. If we consider pinion material is steel and gear material is steel, then K is equal to 0.16 into BHN upon 100 bracket square. This is in Newton per mm square. And if we take cast iron, if we consider the cast iron pinion and cast iron gear, then K is equal to 0.21 into bracket BHN upon 100 bracket square. And for different types of combination, that is for steel pinion and cast iron gear, or cast iron pinion and steel gear, then for that combination we take K is equal to 0.18 into BHN upon 100 bracket square. This is in Newton per mm square. So this is here we finish our second step. So if we in the up to here we get FB value and FW value. So as module is not known, so we get both the values in terms of module, that is FB is equal to some value into m square, and wear strength equation FW is equal to some value into m square. So we can easily compare FB and FW. If FB is less than FW, then we focus on bending case for designing. If FW is less than FB, then we consider wear for next designing. Next step is third step, that is effective load on spur gear tooth. Actually two different equations are available for calculating effective load. First equation is preliminary estimation method and second equation is precise estimation method. Why it is called as preliminary estimation method? Because at this stage we don't know the dimensions of gear, so this equation is called as preliminary estimation method. And here we consider the dynamic load by using this factor kV, that is velocity factor. So F effective is equal to Ft max upon Kv, but Ft max is Ka into Km into Ft, where this Ka is application factor or service factor, Km is load distribution factor or load concentration factor, Ft is tangential force. Now we see this factor one by one. For calculating application factor or service factor, this table we actually two tables were required. This is the first table number second, that is application factor K. Here the headings become prime mover, which type of prime mover we use for transmitting the rotation. Then duration of service, that is hours per day, and driven machinery, that is uniform, moderate shock and heavy shock. For uniform, moderate shock and heavy shock, another table is there. So that we get the information that in case of uniform, what is considered in moderate and heavy shock, which type of machines are considered. So for example, if we use the prime mover as electric motor, and our duration of service duration of service